Sharpener breaks off.
Damn it. It was not me.
No, I don't.
All right. So are there any questions? Nobody asked me to upload the video over the weekend, so I'm assuming nobody actually did any studying over the weekend.
No, we're just studying. We forgot to
Studying
ask.
tomorrow. That's what I'm doing my studying tomorrow. Right
Are there
before the
any-
test, cram it.
Are there any questions regarding the first exam? No questions? Yep, go ahead.
Will you be uploading a video between now and Thursday?
Yes. Yep. Especially if you remind me to do it, I definitely do it. So make sure you bring, pencils and also, erasers and rulers. Anything that you need to take the exam. Make sure you bring it on Thursday. I have had students, one particular student, who took this class, some in the past semester. I won't tell you which semester. Otherwise, you guys can start to pinpoint people. I think, that's him or her or whatever. So anyway, this student, did not bring along anything for an examination. So the student was asking other students, "Oh, do you have a pencil? Can I borrow your eraser? How about your ruler too?" the whole time he was just trying to borrow stuff. Now he wasn't, this person was not cheating. I knew for sure that he was not cheating. However, it was quite distracting to other students that he has to keep borrowing stuff, all over there throughout the entire exam. So I want you guys to make sure that you bring along your writing instruments. Pencils work best, okay, because you can actually erase it, when you need to. So bring along pencils, erasers, and in case one pencil breaks or something, and you cannot use it anymore, bring along like several. Okay, mechanical pencils work great, unless the pencil itself break. All right. So let's go ahead and get started. We got started with hierarchical or top-down design already. So we'll just go ahead and continue with that topic today. And this is the first time we'll actually start to write programs. We'll actually start to develop an algorithm in the class to solve a problem. So it's really hard to teach the process of writing a program, but I will try my best to illustrate what goes through my mind when I need to write an algorithm to solve a particular problem. So today's lecture is mostly about that. It's not something that we haven't seen before. It's more like how do we apply things that we have already learned in order to actually start to write algorithms. That's kind of the focus of today's class. Okay. As we wait for Moodle to load the screen, how many people still remember how to factor numbers into its prime components? Like 15 is 3 times 5. So most of you still remember how to do it. So we'll go ahead and get started with that one because that's the problem that we want to solve today. And the first thing we want to do is just do it manually, and then we'll try to do it using an algorithm. So we are basically on topic 6 right now. The practice exam here really doesn't apply because they're all kind of grayed out from previous semesters. If you guys want more practice, I can certainly unhide these. So now you can actually see them. But I think the practice exam that we went through last week, was already sufficient. All right. So I'm just going to go to the notes here, but I'm not going to talk about the notes or read from the notes itself. What I'll do is I'm going to use an example. I usually go for the whiteboard, but I really should stop doing it because it's much better to do it here on the computer. And then before we go any further, I'm going to start the upload of one of the videos that I captured last week, just so that I can delete the file later on, and then I'll have space on the hard drive to make sure that we don't miss anything for today. All right, so let me log into YouTube and sign in. I'm uploading the notes from last week's 310. Because otherwise my little flash drive may run out of space pretty quickly. All right, so that's out of the way. And now we can move on and talk about today's topic. All right, so let's go ahead and try to factor a number into its prime components. This is one of those things when you use a very simple example, you really don't get much out of it because you can use the eyeball algorithm to solve the problem. I'll give you one example. Let's try to factor out all the prime components of this number, 30. Okay. Most people look at this and go like, oh, at least I know there's a 2, there's a 5, and there's a 3, and we're done. Does it really show you the process of finding the prime components of this number?
Nope.
Not really, because we can eyeball everything. Now, we can eyeball everything because the 2 and the 5 are very simple because it ends, the least significant digit is a 0. That means it's divisible by 2, and it's also divisible by 10, which means it has 2 and a 5. Once you divide it by 10, you have the 3, and we are done. So it's way too simple. It doesn't really illustrate the process of finding a prime component of a number. So what we need to do is to start with something that's at least a little bit more challenging. So let's start with something that's more like this. Okay. Well, all the simple rules that we know do not apply anymore. And frankly, I don't even know whether this is a prime number or not. I really don't. I just randomly pick a number that is not obvious whether it is prime or not, and it's a good way to start to work on our algorithm. In other words, when you need to start with your algorithms and you want to see how you can solve a problem by hand, don't give yourself trivial examples. Give yourself some really real examples where it is challenging and you cannot just use rules of thumb or heuristics to solve the problem. Let's try all the heuristics that we know about factoring numbers. Is this number divisible by 2?
No.
No, because it ends with a 1. Is it divisible by 3?
Nope.
No, because when we add up all the digits, they don't, it's the sum of the digits is not divisible by 3. Is it divisible by 5?
Nope.
Nope. So I think I ran out of all my tricks. Do you guys know any other tricks that I don't know? No? Okay, so we just have to do it the hard way, right? Now, what do I mean when I say do it the hard way?
Try every possible combination until you come up with something.
Well, we can try it systematically. So instead of trying something, instead of using an approach like lotto, like let's try 23, and then next we try 37, and then we try 41, and then we go back to 17. Instead of doing that approach, maybe it is better to do it more systematically, starting from the smaller numbers, right? All right. So what we'll do is, I'm not going to do all the division because I'm really, really bad at arithmetics. So I'll leave it up to a tool that is much better at that particular task. Spreadsheet. That's what spreadsheets are for. All right. So we have a number here. It's 3001. And then what we'll do is to look at the remainder of this number divided by a potential factor. So we'll go ahead and, well, I'll even label the columns. How about that? Okay, this is the number n. This is a potential factor. And here we have the remainder. Okay. So I know this is not very smart, but I'll do it anyway. We'll start with 2. To you and I, it is kind of dumb to look at 2 as a potential factor because we have that rule of thumb and say, hey, anything that ends with 1 cannot possibly be divisible by 2. But you know what? It's just one number, and in the grand scheme of things, this is not really that big of a waste of time. So we'll go ahead and do it. And to find the remainder of something, in a computer, there's an operator called a mod operator. Mod stands for modulus, M-O-D-U-L-U-S, modulus. And what it does is it finds the remainder of a division. In other words, when you normally say 24 divided by 7, you usually get the quotient out of the division. And this only gives you the remainder of the division. Okay, so when you say mod, you give it 2 numbers. In this case, the first number is this number here. And because I'm using a spreadsheet, it's really quite helpful because I can just say, okay, just refer to that number. And then the second number is the potential factor. In this case, it is the cell B2. So now I'm dividing 30,001 by 2, and this gives me the remainder. Are we doing okay so far with what I'm doing here? Okay. And here I will use a 3. And what do you think is the remainder of this number divided by 3? That's an easy one. It's another 1, right? Because 30,001 is very, very close to 30,000, and if you divide 30,000 by 3, you get a remainder of 0. So this one is just 1 off from it, so it has a remainder of 1 as well. So from here on, I can just be a little bit lazy and try out all these things. Okay.
Quick question: what was the mod command again? I didn't catch it.
That's okay. It's mod,
Okay.
and then the first number is the dividend. The second number is the divisor. Yep.
What dollar sign for this?
The dollar sign means do not make that number change as the formula is copied. Because if you look at the other ones, okay, do you see the difference between this one and this one here? You can see the reference to B2 is changed to B11. In other words, as I copy and paste the formula, if I don't use a dollar sign, the referenced cell will also change relative to the formula where you copy and paste the formula. If you put a dollar sign, it means absolute reference. So that means that will not change as you copy and paste the formula. It's a really nice, great little tool to use in a spreadsheet. All right. Someone is going to say, but it's just wrong to test it with 4. 4 is not even a prime number, and I'm only interested in finding prime factors of this number. Well, I may be slow and dumb and also not very efficient, but am I wrong? Is it possible for me to mistakenly identify 4 as a potential factor of that number when I have tested 2 already and 2 is not a potential factor? It's impossible.
No.
Okay? So that means trying 4 as a potential factor is a waste of time. It is not the best thing to do, but at the same time, it is not wrong either. Okay? Does everybody understand the difference between inefficiency and in being incorrect? One does not imply the other. Okay? All right. So the question now is, when do I stop? Well, I guess if when we find a 0, we can stop for sure. Okay? So we'll just keep going. And obviously this can be, since I pick a number that I have no idea. Okay, let's see if there's a 0 here. You know what? I'm going to do this. Is that 0? Oh, right there, 19. All right. So if you were to do this by hand, you would have to go through these numbers until you test 19 as a potential factor. Once you find 19 as a potential factor, are we done? No, because we have found one factor of 30,001. It doesn't mean that that's the only factor, right? So what we have to do in the next spreadsheet is to do something similar, except we say this is 30,001 divided by 19, which itself looks like a pretty nasty number too. So we'll go ahead and do exactly the same trick as in the first slide here. So I'll just copy and paste. Oopsie. Switch the tab here, and then we'll do the same thing here. All right, let's take a look. Is there a 1 in there? Anywhere? Okay. Now the next question is, when can I stop? Can I stop now? When I have tested up to 79? Well, I don't know yet, because remember my math is really bad. Okay, I think we can stop now.
It's too high.
I think I can stop because when you look at the potential factor, 80 or 79, whichever one you want to pick, it's pretty close to 6,400 already. And 6,400 is more than the number that we want to find a factor for. And at this point, I know for sure this number, the number itself, which is 1,579 itself is a prime number. I can conclude right now. I don't even have to finish the test, because the square of the potential factor is already greater than or equal to the number that I'm testing. That's enough for me to say, oh, it's time to stop. If there's no factor found at this point, there won't be any factors. Okay, I'll explain why that works. Okay, intuitively it makes sense, right? Just think about it. If you think a number is a composite number, in other words, it's a product of two smaller numbers, one of the factor has to be smaller than or equal to the square root of the number itself. Does it make sense? You can try out some examples. Okay, let's try out, let's say 45. Okay, so if you look at 45, the factor is 3 times 15. 3 times 15. The square root of 45 is between 6 and 7. Let's say it's 7. Okay, this number is less than or equal to 7. Okay, let's pick some other numbers. Let's pick 121. 121 is 11 squared. But 11 itself is less than or equal to the square root of the number. Okay. You guys want some more examples? 63. 7 times 9. 7 is less than or equal to the square root of 63. So we can always know for sure, if you cannot find a factor by the time you get to the square root of that number, we know there won't be any factors other than the number itself, which means it is a prime number itself. Yep.
That's a definition, like it's always true.
It is always true, yes. In fact, since I introduced this topic now, I'm just going to change the organization of the class notes a little bit, and I'll explain why this works first. I'll prove why it works, and then we'll go back and work on the algorithm itself. So instead of using the algorithm already in the notes, which is not a very efficient one, we'll work with the one that is a lot more efficient. Okay, so I'm changing the way the notes is organized just a little bit because I'm changing the introduction of the material. Okay, so what I'll do is I'm going to prove a theorem. You are not going to prove theorems in your examinations. So there's no theorem proving whatsoever in your test. But I do want to show you the importance of knowing something for sure. Okay? So we'll start with my claim in this proof here. Tag claims, and I'll put it in uppercase. Claims that, okay, for any number n such that you can divide n into a times b, and a is greater than 1 and b is greater than 1, n is n, oops, a, b, and n are all non-negative integers. The following must be true. Okay? So this means, you just pick any number. You pick any number a, which is an integer greater than 1. You pick any integer b that is greater than 1. I will define n to be the product of those two numbers. The following property has to be true. Okay? This property says, a times a has to be greater than or equal to b, or b times, oops. There we go. B times b is less than or equal to n, sorry. There we go. Okay, this is my claim. The first part, there's nothing to prove. Okay, this part here, there's nothing to prove here. These are given. In other words, you are free to pick a and b. Okay, just pick any integer a, pick any integer b, but they have to fulfill these requirements. A has to be greater than 1, b has to be greater than 1. That's your pick. I define n to be the product of those two integers. Okay, so there's nothing to prove here. These are criteria for your selection of a and b and the definition of n as a result. Is that okay so far? That there's nothing to prove here? There's nothing that may be true or may be false? Yep. Actually, I think it works with greater than, even, or greater than or equal to. So if you want to change it, that's fine too. But I'm just going to keep it the way it is right now.
I'm seeing it's less than both 8 times 8.
You mean here?
Yeah. That's 8 times 8.
Less than or equal to n, or b times b is less than or equal to n.
Okay.
That part is right. Yep. Question? No. Okay. So there's nothing to prove here. This is just a given condition. Okay. You pick a and b. I define n as fulfilling these requirements. But as long as a, b, and n are picked this way, this has to be true. That's my claim, which may be true or it may not be true. Okay. So you guys will look like, okay, well, let's pick some numbers, right? Just like numbers that we have picked already. Let's pick, some really odd numbers like 77. 77, if n equals to 77, then a is 7 and b is 11, right? So is my claim true for this particular case? It is, because 7 times 7 is 49, and 49 is less than or equal to 77. Okay, so that works out. Only one of these two squares has to be less than or equal to the number n. They don't have to be both less than or equal to the number n. Okay, we can pick other numbers. For 121, it works out too, because 11 times 11 is less than or equal to the number n itself. So it still works out. But does it mean that the next number I pick, it will also work out? Not necessarily, right? You can say that, but Tech, I picked 20,000 numbers, and your claim works for all 20,000 numbers. It doesn't mean the 20,001 and the first number after that is going to work also. So what we need is a way to prove that this has to be right for all combinations of A and B. As long as A is greater than 1, B is greater than 1, and n is a product of those two, this has to be right, has to be correct. Okay. So how do we go about doing that? Well, this is not a math class, so I'm just prompting you with that question so that you can start thinking about it. Now, some people will say, but Tack, I'm a programmer. I want to be a programmer, not a mathematician. Do I really have to prove something like that? The answer is yeah. The answer is yes. Well, you don't have to prove it yourself, but you have to have a confirmation one way or another. You can go ask a math professor. You can go ask someone who's good at math. You can also look up books, Wikipedia, stuff like that. But you need to confirm this before you make use of it in your algorithm. But why? But Tech, I just tested 20,000 combinations of A and B, and it works for all 20,000 numbers. Isn't that good enough? Only if you work for certain software companies, which I will not name.
Microsoft.
Okay, because just because it works for 20,000 or 20 million or 20 billion numbers does not mean it is always true. Okay. I'll give you one example of one story that will basically set this right. Years ago, we're talking about years ago. I was working on my dissertation, and my dissertation is just basically a long mathematical proof of something. Okay, and I was given the work of somebody else's master's thesis as a basis. So my advisor told me, hey, Tack, just start with this. There's no need to repeat the work that has been done already. So you can start with these assumptions because somebody else has already worked out the math for that portion. And there was one theorem saying something about some property about some kind of solution. Okay, and I looked at that and go like, well, that kind of makes sense. And then I started to work on my own dissertation based on that theorem. Thinking, yeah, that seems to be right. And then weeks into that, 2 or 3 weeks into starting with my own work based on that theorem, I started to have doubts. It's like, I'm not quite sure it is true. It's just a gut feeling, right? So I went back to my advisor and said, are you sure this is right? Because I just don't get a feel. I don't get a solid feeling that this has to be right. Okay. And then my advisor told me, Tack, you can go back and just look at, just read this guy's master's thesis and look at his proof and be confirmed, then you can feel comfortable about using that result. So I did. I went back and read the master's thesis of this person, who coincidentally had exactly the same advisors and the same committee as my dissertation's committee, which kind of put me into a tight spot later on, but I'll explain that later. So I read it, and the proof of this theorem was obviously has to be true. That was it. There was no step-by-step derivation. There's no step-by-step proof. There was nothing. It was just obviously this has to be true. And I was going like, well, that's not enough for me. I mean, it may be enough for some people, but it's just not enough for me. So I spent a whole week, just kind of working on this, and I finally, came up with a counterexample. A counterexample is a specific case to prove a theorem is wrong. How many counterexamples do you need to prove something is false?
One.
You just need one. And I found that one. I found one counterexample to prove it wrong. So I took the counterexample back to my advisor, on the following Friday. We always meet on Fridays. My advisor looked at it, looked through my proof, looked through my derivations, and go like, oh, that was the only reaction. So I took that result back, and showed it to my lab mates. We have a few people working on, master's thesis based on the same theorem, and that guy just went ballistic. He went ballistic because his own master's thesis was based on that theorem too, and he's almost done. He's already more than 2 years into his master's thesis, and he's pretty much almost done. He was months away from getting the whole thing done. It's just getting people to sign off the paper, fixing up some minor issues with formatting and stuff like that. And this changed the whole thing, right?
Wouldn't you be pissed though too?
Huh?
Wouldn't you be pissed too?
I guess I would, but I would have, asked for confirmation first. Exactly. So that was just one story why 20,000, 20 million, and 20 billion examples of how it works is not enough to convince me that this has to work. So mathematical proof is the only way to go to give yourself the comfortable feeling that this you can rely on this fact when you use it in your algorithm. Okay? Are there any questions about this part? I mean, why we have to kind of go through mathematical proof for something that is kind of, it seems to make sense? No? Okay? Can you imagine someone putting an optimization algorithm or an optimization technique that is not proven into some really expensive or really important instrument, like a probe that we send to Mars, or ICBMs,
Or like the Hubble telescope when they put the wrong glass in it.
Yep. Well, we lost one Mars probe because I think it was a unit conversion problem. I think it was one of the which one was that? Does anyone remember the name of that? It had to do with the rockets, to slow down the probe when it's descending on Mars, and I think the unit to specify either the thrust or the acceleration was there was not an agreement. Okay, one party was using like feet per second or something metric. One person was using US SAE units, and then the other person was using SI units.
Oops.
But when you write a program, you don't write down the units, right? You don't say 300 feet per second or something like that. You just say 300. And so the program, basically was using the wrong units, and I think the probe just crashed because of that. Yep, silly things that we do and make it.
That'll get you fired.
Yet you sued, you have to pay for the probe, right?
Yeah, I got $1 billion back.
Or they will send you as the first human colonist to Mars.
Yeah. Using your program.
It's an honor. It's an honor. All right, so let's see how we can prove this. Okay, the technique to prove this is right is actually a very common technique of proving something. It's called proof by contradiction. Okay, proof by contradiction goes like this. Okay, the proof by contradiction says, focus back here. Let's say tag was wrong, and we'll see what happens. Okay, so if I'm wrong, that means even if n is a times b, and a is greater than 1 and b is greater than 1, and they're all integers, okay, based on the same assumptions, somehow this is not true anymore. Okay, that's what happens when when my claim is wrong, my claim is false. Is that making any sense? Okay. Okay, that means, so I'll just copy and paste here, is false for some combinations of a, b, and n. Okay. All right. So let's take a look at this part here and see what we really mean when we say this is false. A times a is less than or n, or b times b is less than or equal to n is false. Okay. So now we're going to go through some algebra here and see, well, to say this is false is to say what is true.
False.
Okay. Well, they both have to be false. Very good. So that means they both have to be false. But okay, let me just propose this, and then we'll talk about the proof of that. Oopsie. B times b is greater than n is true. Do you think these two lines say exactly the same thing?
Yes.
Yeah.
They say exactly the same thing. To say, a times a is less than or equal to n, or b times b is less than or equal to n has to be false, means a times a has to be greater than n, and b times b has to be greater than n has to be true. Okay? Is that okay? All right. So once we can accept this fact, we can then say, well, okay, what about a times b times b? Wouldn't that be greater than n times n as a result? In other words, we know all the numbers are non-negative. Okay, we know they're all positive numbers. They're more than 1. So a times a is greater than 1. B times b is greater than 1. N is greater than 1. B n is greater than 1. Right? So if that is the case, we can just take a times a and b times b and put it on one side of the inequality, and then put n times n onto the other side of the inequality. The inequality should still hold. Is that making any sense so far? Okay. And then we'll go through some algebra here and just rearrange things a little bit. Because after all, what do we know about a times b?
Equals n.
That's right. Okay. So I'll just go ahead and make it very clear what we are doing here. So that means we end up with n times n is greater than n times n. Now, not only are we saying that n times n is greater than n times n, we are saying that this has to be true. Because what I'm missing, being a little lazy here, is we are saying that every single statement has to be true. Right? But what do we know about n times n is greater than n times n?
False.
It has to be false. So this is a contradiction. Because this is something that normally has to be false, but because of where does this all start? Why do we have this big mess up here?
Because we're trying to prove your theory.
It's because based on the assumption that I was wrong. So if the assumption that I was wrong leads to a contradiction like this, what can you say about the original assumption?
You're right.
It has to be true. Okay? That's it. That's the nature of proof by contradiction. Okay? You make the assumption that the theorem was wrong or false to begin with, and then you go through a whole bunch of derivation, and you get to a contradiction, and that means the original theorem has to be true. Okay. So, yeah, go ahead.
Can you explain why you switched from or to and?
Okay, that's a good question. The question is, how do we switch from this to that? That's the question, right? Okay, to understand that, let's look at a more general version of this. Okay, so we'll just take two Boolean expressions. We'll call it E and F. Okay, so E and F, the original thing is to say E or F like that. Okay, so my claim is E or F is the same thing as saying not E and not F, and then put a big negation on the outside. Okay? This is only my claim. I'm not saying that they have to be exactly the same thing, but I'm saying that E or F has Boolean expressions on E and F. This means exactly that. Now, I know this one looks kind of messy. I mean, we have 1, 2, 3 negation and 1 conjunction instead of just 1 disjunction. But the idea is, are they really saying the same thing? Okay? But I can prove this one. This proof is much easier than the one that we just went through. Okay? And that's because of the nature of Boolean logic. In Boolean logic, a lot of times you can prove something just by looking at all the possible combinations. Okay, so let's take a look here. E is a Boolean thing, so how many values can it possibly have? Two possible values, right? Either true or false. Okay. So let's say E is true in the first 2 cases, and it's false in the next 2 cases. When E is true, what can be the value of F? True or false, right? They're 2 independent variables. So when one is fixed, the other one can change any way it wants. But even so, it only has 2 possibilities. It can either be true or false. So we have true, false, another true, false here. Is everybody convinced that we have exhausted all the possible combinations between the 2 Boolean values, E and F? Okay, I really should not have picked F here because F also represents false. So we'll go ahead and make a change here. Instead of F, we'll use G. And I can't really do the global search and replace because this editor does not have a scope limitation when I do something like that. But this is okay. Okay, this is the easy part. When E is true and G is true, what is E or G? True or true is true. True or false is true. False or true is true. False or false is false. Okay. There we go. Yeah, typing, not my strong suit. Okay, nothing is my strong suit. I'm just using that as an excuse. E is true here. What is not E?
False.
False, right? Not E. Okay, E is true. Not E is false. G is true. Not true is false. So we have false and false, which is false. But that's okay because we have a big negation on the outside. Not false is true. Okay? And then we'll do the same thing here on the second row. On the second row, E is true, not E is false. And if you have conjunction, one side is false, you don't even have to bother to look at the other side. So the entire conjunction is false, but not false is true again. So this entire thing is true. Same thing here, we just flip the side to the other side. This is the only case where it is also going to be false, because let's see what's going to happen here. E is false, not E is true. G is false, not G is true. True and true is true. So that means the conjunction gives you a value of true, and the negation of true is false. Okay? What we have just done is to illustrate for all possible combinations of E and G, E or G, which has this column here, is identical to the column that we derived from the negation of E and G over the conjunction to join them. Okay? But how does this connect to what we just did? Well, let's take a look. Let's take a look at what we have originally. This is based on the assumption that I was wrong. Okay? Remember in proof by contradiction, We assume that the original claim is false to begin with, and then we'll see what happens. Does it make sense that if I put a negation on both sides, that the equality will still hold? If I say not the left hand side, and then I say equals to not the right hand side, it will still be right?
Yep.
Okay, so let's go ahead and do that. So I put a not to the entire. Well, let's not do that first. Okay, let's do something else. Let's apply this rule right away. Okay, so E becomes our A times A is less than or equal to N, and then G becomes our B times B is less than or equal to N. Do you think that template works? It fits, right? I mean, we have a disjunction, and we can fit it into the other big mess. Okay, so what we'll do is we'll just plug in the big mess here, and we are not changing the true and false value, so we have to say it is still false. Except in this case, our E is really this expression, and our G is really that expression. Okay. I know it looks really messy. We'll clean it up a little later. Okay. But is it making any sense so far? Does everybody understand how I can make the transition from this expression to this expression once we have this established? Yes? Yes. It's the same thing. Okay, it's the same thing except E and G both become each becomes a more complicated expression. Okay, so let's see what we can do here to simplify our really kind of messy expression here. And this is the way I usually do things, so that I can make sure the level of parentheses are correct. Okay, let's look at this one here. The negation of this is what? What is a convenient way to take the negation of that by changing just the comparison? Turn the less than or equal to greater than. Okay. So that means I can do something like this. A times A is greater than N. Does everybody agree that this is the same as that? When I say it is not the case that A times A is less than or equal to N, less than or equal to N, it's really the same thing as saying A times A is greater than N. Yep. Okay, so we can do the same thing with B. B times B is greater than N. Okay, so we're getting closer to what we actually want the whole thing. If I put a big negation on both sides, that should still work out. It's just like in arithmetic algebra, you can put a negation on both sides in a equality equation, in the equality, and the equality should still hold. So that means I can copy and paste this entire mess into here, and this rather simple thing into here, and the equality should still be true. Okay. This looks like a big mess, but it really is not, because we have the negation of the negation. What do they do to each other? They cancel out. So that means on one side we only have the conjunction left, and on the other side, what is not false? Not false is true. So we got back to this one here. Okay. Now, when you're starting out, this is what you should do, is to go through step by step, derivation, so you don't miss any step in between. How many people have to take CISP 440 to get your degree? Do you guys not know whether you have to take it, or you know that you don't have to take it?
I don't know.
You don't know. Okay, let me rephrase that question. How many of you here are in the computer science degree program? You have to take CISP 440. What is it? It's called discrete math, discrete structure. Discrete structure is the name of the class, but it has nothing to do with structure. It really has to do with math. And
Like
this is
that, pretty much?
Oh, this is like the first 3 minutes of that class.
Sounds fun.
Yeah, the rest of the class is just more and more theorem proving, proving things are right and so on and so forth. Okay. And that's considered a lower division class at a 4-year university, and that's how we can offer that here. So they have follow-up classes at a 4-year university, the upper division classes over there, that is based on this stuff.
Wow.
All right. Okay, so I think by now, we have a fairly good feeling that what I claim here is true, right? Okay, so let's kind of take a step back from all the mechanical steps, all the things about all the things that we have talked about, and just look at how this is going to impact our algorithm to find a factor given a particular number n. How do you think this helps? Do you guys still remember the spreadsheet? Let me just pop the spreadsheet back up here. Okay, this is the number. 1579 is the number that I want to find a factor for. I do not know ahead of time whether it's a prime number or not. I go through the combinations. Now you can also see now why I just let 4, 6, 8, 9, 10 to remain here, because I don't have to find all the prime numbers. It's much easier this way. I just test the next number available. I can simplify the logic quite a bit here. The question is, when do I stop? Now that we know 1579 is a prime number, where do we stop and confirm it is a prime number? Now, if you want to go the old traditional way, you pretty much have to keep going like this. Yeah, we find it now. Oh, it is a prime number because the only way, its only factor is itself. That's how we confirm it's a prime number. So that's a little bit of calculation there. We have about, we have 1,579 divisions in order to get to this point. Well, okay, 1,579 minus 1 because we don't try 1 as a potential factor. We start with 2. Okay, big deal. My alternative approach is to get back here, and then we use the square. Whoops, not that one. We use the square of the potential factor as an indicator of when can we stop. So if I try it this way, I can stop a whole lot earlier. I can stop. What was the number again? 79. With this approach, I can stop right here. Okay. So after 40 divisions, I can stop, versus 1,500 and something. Okay, is that a lot of saving?
Yeah.
Is this method better than testing just the prime numbers? Okay, let me give you the alternatives. One approach is to say, well, we should only test prime numbers. It's just stupid to test 4, 6, 8, 9, and so on and so forth. So I'll just go ahead and make the program more complicated with a table of all the prime numbers. Okay, that's one approach. The other approach is to do it the lazy way and say, well, I'm just going to test sequential numbers, but I'm going to stop early, like this. Which approach will save you more in terms of number of operations? The second approach. This approach will save you more, even though it looks really dumb. I mean, why do we have to test 39? I mean, 39 is a composite number. But even so, this approach is a whole lot faster. Okay. Well, does it work better with even larger numbers? I mean, are we going to save, computation time for bigger prime numbers? In fact, the bigger the numbers, the more we're going to save. Because we are comparing the root of a number to the number itself. So the larger the number, the difference between the root and the number itself becomes even larger. Okay, so this is in fact a very good optimization technique. Any other questions? Nobody asked the question why we don't use the square root of the number. Instead, I just multiply the potential factor by itself. Nobody asked the question, but I'll answer that question anyway. Multiplication is cheaper than square root. That's why. In other words, with most computers, it is less expensive in terms of computation time to find out what is the square of 2 integers than to find the square root of an integer. Okay? So that means, but I only need to compare. I really don't need to know the square root of the number. All I want to do is to compare the square root of the number with the potential factor. So one way to do it is not to find the square root, but to, well, I guess if you find the square root, you only have to find it once, and then you can do the comparison, throughout the operation. So that works out too. All right. So now that we have these tools, let's go ahead and write an algorithm. Okay. So our next task is to write an algorithm to find a factor, prime factor, f of a given integer n. And let's just say that I guarantee that n is greater than or equal to 1. Yep.
You mean not a 1?
Oh, yes. All right, there we go. So this is our task to actually write an algorithm to solve this problem. The problem is I give you an integer, and I give you an integer n is guaranteed to be greater than or equal to 2. Your task is to write an algorithm to find a prime factor f of that number. That's all. Okay. How would you do this? Well, you look at all the tools that we have. It's just like building Lego, toys and whatnot. When you want to build something, you kind of have to start with, okay, what blocks do I have? What are the tools that we have already? We have conditional statements, we have assignment statements, and we have loops. Okay. So my first question to you is, do you think this process is somewhat repetitive?
Yes.
It is kind of repetitive because if we look back at this slide here, does that look kind of repetitive to you? Yeah, it looks kind of repetitive. So when it is repetitive, okay, so this is revision 1 of the algorithm. When I see something is repetitive, I just say, oh, okay, there has to be a loop in there somewhere. So I'll just say loop and loop. But we haven't really talked about the programming construct called loop and loop. Well, this only means it's a generalized loop. We don't know whether it should be a pre-checking loop or post-checking loop. We just know it is some kind of a loop, and that's what I used here as a notation to say that it's some kind of a loop. It has to do something repeatedly. I have no idea whether it is pre-checking or post-checking. I just know that we have to do something over and over again. Okay? And when can we get out of the loop? If you look at the examples here and the example here, when do we get out of the loop? Let's try without the optimization first. Okay? So without the optimization, when do we get out? When the remainder of n divided by the potential factor is 0. Is that making any sense? Okay? So we'll go ahead and just write that here. Okay? When n mod f equals to 0. Once again, the mod operator is kind of like division, except we don't get the quotient out of the division. We get the remainder out of the division. Is that okay? Okay. It's in the notes too, but since this is the first time we talked about it in the class, I'm just going to make sure that we understand what the mod operator is. Okay. And you know what? I'll call this revision 1. That's it. There's not a whole lot in it, but it's enough for me to get started. Okay? Is that okay so far? Does everybody understand, that I'm just starting out with the structure of the algorithm? There's a lot more details I have to specify later. Okay. Now that we know the exit condition is when n mod f equal to 0, the next question is, which one is, are they both going to be changed, or which one is going to be changed in the loop? When we do something over and over again, something has to change. Because if you don't change anything, if n mod f does not equal to 0 to begin with, and you're not changing n or f, that means it will remain the same condition the whole time. If it does not equal to 0 the first time, it's not going to be equal to 0 the second time, and this becomes an infinite loop. So that means inside the loop, you have to do something about n or f or both. Does that make sense? Okay. But n you cannot change because it is a part of the problem itself. You are given n and you're supposed to find f. So that means we are only allowed to change f.
Yeah, so you do f plus f plus 1.
Okay, our approach here, if you look at our example, is we just start f with 2, and then in the loop we just add 1 each time to move on to the next available integer. Okay, so we'll go ahead and just do that. So now we have revision 2. So in revision 2, we specify what is in the loop here. And we just say that, well, we'll just go ahead and increase. Oh, I just said not to change n. So we're changing f, and increasing it by 1 for each time. And we'll call this revision 2. I have to change that number there.
Shouldn't we specify what f is to begin with?
Yes. In revision 3, we have to do it. Okay? Because in revision 2, we know which one we're supposed to change, and we kind of have a good feeling that eventually f will become the same as n, and at that point it has to exit. We know the algorithm has to exit at some point, even for prime numbers. And then the third, in the third revision, we go, well, but what do we start f with? What is the initial value of f? Now that turns out to be a kind of tricky question, because we still haven't answered the question of, is this a pre-checking loop or a post-checking loop? And in this particular case, it can actually go either way. Okay, so we'll go ahead and take a look. We'll answer both questions in this revision here. I'll call this revision 3a, which means it's one alternative of the two. In one alternative, we turn the loop into a post-checking loop, because it kind of looks like a post-checking loop here. Okay, we say repeat, and then we say until, and we're done. Because the condition is an exit condition, and it fits the template of a post-checking loop. So in this case, how should I initialize f? In other words, what is the first value of f?
2. 1.
It has to be 1.
F plus 1.
It has to be 1 because it's a post-checking loop. So that means the body of the loop has to be executed at least once before we get to the condition part. If you start with 2, then this will bump it up to 3. So by the time you test it, you would have missed 2 already. So that's why we have to start with 1, because it's a post-checking loop. That's revision 3a, which works. And here is revision 3b, which also works, because this one is using a while loop, which means as long as. How should I rewrite the condition in a pre-checking loop? Remember, while means as long as, so how should I say it in this case? That's not equal to, right? Okay. All right. But in this case, how should I initialize f?
The 2.
In this case, I initialize it with 2. Okay, so we have 2 alternatives. They both work, they're both correct. But one is better than the other one. Which one is better?
Pre-checking.
The pre-checking one is better. How is it better?
Because you don't have to run the operation if you don't have to.
Okay, you can save one addition, because you don't have to go into the loop if the first one is false to begin with. You can exit right away. But that's not the main reason why we prefer the second one. Yep.
Because we're assuming n is a positive integer.
Well, it's already given to you that n is greater than or equal to 2, n is an integer. Yes. Okay. The second one is better in a different way. From my perspective, it is better because it spells out very clearly what is the first prime number we're going to test. It is completely spelled out as 2. Whereas in the first algorithm, we put a 1 into it, which is kind of misleading because that's really not the first value that will be tested, because it's a post-checking loop. So by the time we get to the until line, f would have a value of 2 already, even in the first iteration. Yep.
Why don't we ask if f is different from 0? Why don't we just say f is greater than 0?
It's the same. Yeah. In this case, you can also. It's because this is a direct negation of that one. That's the only reason. Because we want to make sure that when you write, when you turn an exit condition into a as long as condition, we keep the condition pretty much the same and only add a negation to it. In this case, yes, it makes sense that you can forget about the less than, because we're only dealing with non-negative numbers. But because not equal to is a direct negation to the equal to, and that's the reason why we take this one. It doesn't actually take more time to compute either. the not equal to comparison takes exactly the same amount of time as the greater than. Okay, so now we know that 3b is our preferred solution. Okay. The other one is not incorrect. It is just less self-documenting in a way, because when you look at the code, it doesn't really quite tell you directly what is the first number we're going to test it with.
Do you need to put anything in to separate 3A and 3B?
Well, sure. We'll use a thinner line to separate those two. Okay. But this is not the smart way of doing things, because this algorithm is going to look like sheet 2. In other words, we'll keep testing and testing and testing until f becomes the same as n, in which case we will find the remainder to be 0, and then we get out of the loop. So the next question is, how do we integrate the optimization that we want to put into it?
Or
Okay. Well, let's take a look here. Okay. So to optimize this a little, we can make use of the theorem proven a little while ago. Okay. The first question is, with that optimization, am I getting out of the loop earlier or later?
earlier.
Earlier. So I want the condition to be false earlier. Okay. How do you make the condition false earlier? Do you use a conjunction or do you use a disjunction?
Conjunction.
And
Okay. You use a conjunction. You use an and, because when you have an and, that means now you have two reasons to get out of the loop. Because if any one of the two conditions becomes false, the entire conjunction is false, and you get out. So that means, for an optimization technique like this one, where you want to get out of the loop earlier, and this is a pre-checking loop, you want to use a conjunction so that you have more reasons to get out of the loop instead of using an or, which means more reason to stay in the loop. Is that okay? Is that making any sense? Okay. In the optimization that we want to do, we are trying to get out of the loop earlier, not later. The condition has to be true to stay in the loop. So we are trying to make the condition false earlier to get out of the loop. Now the condition that we have already still has to be there, okay? Because we can find an actual factor, so n mod f will still have to be checked and see whether that's 0 or not. But we want to be able to get out earlier, which means there's a second reason to make the entire condition in the while loop false, right? So to increase the chances of that condition being false, we cannot use a disjunction, because in a disjunction or, both conditions have to be false for the whole thing to be false. But in a conjunction, if any one of the two conditions is false, that's good enough for me. The whole thing is false, and we get out. So that means we should use a conjunction or an and in this case to optimize it. All right. So let's say and blah blah. Okay. So what else has to be true to stay in this loop? Let's take a look at our example here. Now, see, this is why it is so useful to kind of work out a simple example first. Let's see, where is that slide? Oh, right here. Okay, I claim that we can get out by the time we get here. So how do you translate that into logic in a program?
F is smaller than important.
Sorry?
F is smaller than important, or less than important.
F is less than or equal to the square root of n. Okay, it's all about n and f. Okay, so there are two ways to express it. You can express it as and f has to be less than the square root. This is sqrt is square root of n. That's one way to express it. Or if you prefer not to do that, you can also say the same thing like this. Is that okay? I mean, does everybody understand how those two are? Basically, when you have inequality like that, you can square both sides, or you can root both sides, as long as f and n are both non-negative numbers to begin with. Are we doing okay so far with the optimization?
Yeah, makes sense.
But that's not the end of it. Because this time when we exit early, f is not a factor of n. Think about this, okay? Let's look at this here, and I'll just go ahead and label. This is our n. This is our f. This is our n mod f. And this is f times f, okay? Label all the columns. And we'll leave the columns up here while we scroll to the number that we want, which is down here, right here. Okay. All right. So that means by the time we get out of the loop in this case, what is the value of f at the time? F has a value of 40. But what is the job, what is the responsibility of the algorithm? Its responsibility is not to say whether n is prime or not. That's not its job. Its job is to make f a prime factor of n. So far, it has not done its job yet. So what do we need to do after the loop?
F equal n.
We need to have an assignment statement so that f becomes the same as n, and then it becomes a prime factor of itself. Okay, so that means, but we don't have to do it all the time, because if n is in fact a composite number, then we actually find a prime factor, and then the loop would have done its job already. So that means in our algorithm here, we have to go in two directions. Okay. In some cases, yes, we have to change f so it becomes the same as n. In other cases, there's nothing to do. Okay, so we'll go ahead and finish the template of the conditional statement first. And in the conditional statement, we know exactly what we have to do because n is a prime number, and so it becomes its own prime factor. The question is, what do we put here? How do we confirm that we have just found a prime number?
Divided by f.
Just kind of flip this condition, right?
Yeah.
Flip it around, but not exactly around. It is related to it. It's f times f is greater than n, but not greater than or equal to. Okay? Remember, there are three relationships or three ways f times f can relate to n. You can have f times f being less than n. You can have f times f equal to n, and then you can have f times f greater than n. What does it mean when f times f equals n?
The condition's already, or it's already a factor.
F is a factor of n. So I should not do this part if f times f equals n, right?
Yeah.
So the only time when n is a prime number is when f times f is greater than n and not equal to. Okay, so equal to cannot be a part of that comparison. Are we doing okay so far? Yep.
Never mind. So I was just wondering, so when you're doing if and if, you never do if and then parentheses and then do. You just always use if and then that.
Yes. The do is only in the loop setting. Yep. And that part is kind of a convention thing. It's just conventionally with almost all programming languages, they either do not have the word then, like in C, or in Visual Basic and other languages, they use the word then to follow the if, to indicate the following statement is going to execute when the condition is true. Okay, very good. Well, let's go ahead and test it. Okay. I know we are not supposed to just use test cases to prove an algorithm is correct. So unless someone wants to do it using the pre and post condition and prove the entire thing is correct, we'll just go through one or two test cases and.
I think we all prefer tracing.
Well, tracing can give you a kind of warm and fuzzy feeling, but not necessarily yes, it is going to work all the time. So we'll go ahead and make a folder for this. So I'll save the document just for the derivation and whatnot first, and then we'll work on the algorithm next. sheet, copy and paste the algorithm. And I copy and paste, it doesn't automatically turn that into an arrow. So I have to go through this a little bit just to make it look nicer. So we have our algorithm here. Let me make sure I save at least the algorithm. Okay, find factor and f of n. Okay, and then we'll go through maybe 3 test cases here. Can someone suggest 1 test case that is actually meaningful? Okay. How about one when n itself is not a prime number? I think that might be helpful. Okay. So we'll go ahead and pick some n that is not a prime number. In the precondition, we have to give n a value because otherwise we can't really execute line 2. Let's pick, what do you want? 35? Okay. So we'll pick 35 here. F has an unknown value to begin with because that's the solution that we're looking for, and so it doesn't have a answer yet. We start with line 1. Line 1 puts a 2 into f. We go to line 2. We have to evaluate that rather long condition. So we'll say n mod f does not equal to 0 is that true or not?
True. Absolutely.
Yeah, true is
N is 35, f is 2, so n divided by f has a remainder of, well, we don't even care what it is. Is it 0 or not?
No.
It's not 0, so this condition has to be, it's true. It is true because the remainder of n divided by f is not 0, is true. Okay. So that means we have to look at the second one. F times f is less than n, is that true? F is 2, 4 is less than 35 is true, so the whole thing is true. Okay, so we have to go to line 3. Line 3 adds 1 to f, f becomes 3, and then we go back to line 2. N is 35. 35 mod 3 is what? 2. 2 is different from 0 is true. Okay, so we have to look at the second part of the conjunction. 3 times 3 is 9. 9 is less than n, which is 35 is true as well. True and true is true, so the whole thing is true. We have to go to line 3. We add 1 to it. It becomes 4. This is the dumb one, but it's not incorrect. 35 mod 4 is 3 because the remainder of 35 divided by 4 is 3. 3 is different from 0 is true. 3 times 3 is 9. 4 times 4 is 9. No. Okay, I take it back. It's 16. 16 is less than 35 is true. So we have true and true again. The whole thing is true. So we have to go to line 3. We add 1 to it. It becomes 5. When we get back to line 2, the first condition will say, hey, 35 mod 5 has a remainder of has a remainder of 0. 0 is different from 0 is false. Okay, so here comes a question that will be that we'll investigate a little bit later as well. The question is, well, if we know one side of the conjunction is false, should we even go ahead and evaluate the other side?
No, there's no need to because either one will exit you.
Well, there's no need to, but the question is the C compiler or is a C compiler going to do it anyway? That's the real question. The answer is according to the definition of the C programming language, it does not. It's called a short-circuited evaluation method. In other words, if you can short-circuit out of it, you will short-circuit out of it. So in this case, we only have to evaluate one side. Okay, we only have to say n mod f is different from 0 is false, and we don't even write the other side because we are not going to evaluate the other side. is it going to cause problems if I evaluate the other side anyway, just wasting, is it only wasting computation time, or is it going to give me some incorrect result? That's the question.
Just wasting computation time.
Exactly, because if one side is false, the other side can be true, can be false. We don't care because it's not going to change the result of the conjunction.
Only way it would change it would be if it was an or, wouldn't it? So
Yes, if it were an or, then it would. You have a second chance of making the whole thing true. Yes. Okay, so where do we go? Not post yet. We're not done yet. We go to line 5. Okay, so line 5 has its own job to do. F times F, which is 5 times 5, which is 25. 25 is greater than N, which is 35 is false. That means we really have nothing else to do. We get to post. All right. So then we'll look at another test case. We have just enough time to do it. And this time, we'll look at a prime number because we want to see whether that prime number thing, the shortcut, actually works or not. 7 would be a good one because we have to go through at least a few iterations. 2 is a prime number too, but 2 would be kind of trivial, wouldn't it? Because with 2, we don't even have to go in once. So we'll go ahead and make it 7 just to make it a little bit more challenging. So we go to line 1, we change F to 2, we go to line 2. Then this time we have N mod F being different from 0. This time it is 7 mod F, which is the remainder of 7 divided by 2, which is 1. 1 is different from 0 is true. We have to look at the second half. F times F is 4 in this case. 4 is less than 7 is true. We have true and true, so the whole thing is true. We go to line 3, we add 1 to F, F becomes 3. And then we go back to line 2. N is 7. 7 mod 2 is 7 mod 3, excuse me. 7 mod 3 is 1. 1 is different from 0 is true. So we have to look at the second one. This time F is 3. 3 times 3 is 9. 9 is less than 7 is false. So the second one gives me a false this time. We have to get out of the loop. But we are not really quite done yet because line 5 has its own condition to evaluate. Because this is a good test too, because we want to test whether the conditional statement after the loop is going to take care of that special case when N is prime. So in this case, we say F times F is 9. 9 is greater than 7, which is N is true. So we go to line 6. Line 6 is going to copy the value of N to F, so F becomes 7 as well. Then we get to post. Well, is it doing its job right? In other words, is the algorithm finding a prime factor of N?
Well, the only factor of N is N, so yeah.
Exactly. So it does it gets its job done. Okay, before we leave, we have another minute or so. The question is, what about 1? Is 1 a prime number? Because this algorithm obviously is not going to say, it's not going to report 1 as a prime factor of any number because we start off with 2. So the question is 1 considered a prime number?
Isn't it a special case?
Is a special case, it is actually by definition not a prime number.
Because it's only divisible by itself and 1 it is, so.
Yeah, but 1 is also divisible by itself and 1. But it is by definition that N is not, 1 is not a prime number. So officially it is not. It looks like a prime number, but it's not. Yep.
On line 4, the trace when you change F times F is greater than this or less than 7, shouldn't that be less than or equal to?
Yeah, I should have used the variable name. There we go. Say.
Oh, can you upload the video on YouTube of that?